everyone, welcome back to my channel. This video is particularly about Wilson's theorem. Wilson's theorem states that if p is a prime number, then p minus 1 factorial, which is congruent to minus 1 modulo p. Here, if we consider p as a prime number, then we can consider a congruency as p minus 1 factorial, which is congruent to minus 1 under modulo p. In engineering mathematics, they have prescribed only the statement for Wilson's theorem and problems related to Wilson's theorem. Let us solve some of the problems on Wilson's theorem. Here is the first problem. Find the remainder when 97 factorial is divided by 101. Here this is a problem. Here we have to find the remainder value when 97 factorial is divided by 101. In previous videos, we studied how to find a remainder when some values are given, but here in this case, Wilson theorem is based on factorial method. So, if p is a prime number, then p minus 1 factorial is congruent to minus 1 under modulo p. Using this formula, we can find the remainder value when 97 factorial is divided by 101. First, we have to take by Wilson's theorem, we have p minus 1 factorial, which is congruent to minus 1 modulo p. So, we know that we have to find the remainder when 97 factorial is divided by 101 means p value is 101 here. So, substituting 101 as p in Wilson theorem formula, we get 101 minus 1 factorial, which is congruent to minus 1 under modulo p is 101. Here 101 minus 1 is 100. So, 100 factorial is congruent to minus 1 under modulo 101. Here we have to find the remainder for 97 factorial. Here we have 100 factorial, which is congruent to minus 1 modulo 101. This means minus 1 is a remainder when 100 factorial is divided by 101. But in the given problem, they asked to find the remainder when 97 factorial is divided by 101. So, we have to reduce this 100 factorial to 97 factorial by the formula. We know that n factorial, we can write it as n into n minus 1 factorial. So, this is a formula of factorial. So, in the place of n, we can substitute as 100 here, we get here. We have to achieve 97 factorial. For that, we can use formula over here. Here n factorial is n into n minus 1 factorial. In the similar way, n minus 1 factorial is as same as this n minus 1 into n minus 2 factorial and so on. Here 100 factorial, we can write this as 100 into 99 into 98 into 97 factorial. Because 100 factorial, we can write this as 100 into 99 factorial. 99 factorial is 99 into 98 factorial. The similar way, 98 factorial is 98 into 97 factorial. Here we have to achieve 97 factorial. We have to apply this formula, that is n factorial. We can write this as n into n minus 1 factorial. So here 100, 99, 98 all are bigger values. So to reduce this to a smaller value, we know that 100 is congruent to minus 1 under modulo 101. Here 100, 99, 98 all are bigger values. So to reduce to this to a smaller value, we know that under modulo 101, we can write 100 as 100, which is congruent to minus 1 under modulo 101. This is because by the definition of congruency, we can write this as 101 divides 100 minus of minus 1. Now that 100 minus of minus 1 is plus 1. 100 plus 1 is 101. Obviously, 101 divides 101 satisfies. So, in the place of 100, we can write this as minus 1 under modulo 101. In the similar way, 99, we can write it as 99 is congruent to minus 2 under modulo 101. Because this is also by the definition of congruency, 101 divides 99 minus of minus 2, that is plus 2. Hence, we have 101 divides 101 satisfies. So, in the place of 99, we can substitute as minus 2. In the similar way, in the place of 98, we can substitute as minus 3 under modulo 101. Substituting all these values here, we get minus 1 into minus 2 into minus 3 into 97 factorial, which is congruent to minus 1 under modulo 101. So, we have minus to minus plus, plus into minus minus, 1 into 2 into 3 is 6. Hence, we get minus 6 into 97 factorial, which is is congruent to minus 1 under modulo 101. Here also minus that cancel. Remaining is 6 into 97 factorial, which is congruent to 1 under modulo 101. But here we have to find the remainder when 97 factorial is divided by 101. So to achieve that value, we can divide throughout this by 6, or we can take this 6 to an right hand side. We get 97 factorial, which is congruent to 6 power minus 1 under modulo 101. If we divide throughout by 6, we get the 6 gets cancelled. Remaining is 97 factorial, which is congruent to 1 by 6. We can write this as 6 power minus 1 under modulo 101. So this implies 6 power minus 1 is a remainder when 97 factorial is divided by 101. But here we have to find the value for 6 power minus 1. So 6 power minus 1 is nothing but the inverse of 6. That means we have to find the inverse of 6. Next step, we have to find the multiplicative inverse of 6 under modulo 101. Here in previous problems, we didn't find the inverse for any of the values or any of the congruency. But here we have to find the multiplicative inverse for 6 under modulo 101. To find the multiplicative inverse means we have to note one important statement, that is, if A and M are relatively prime, then an inverse of A modulo M exists. That means if A and M are relatively prime, that means the GCD of A and M value is 1. In that case, inverse of A modulo M exists. This is very important note to solve inverse value for an congruency. So they are given A and M are relatively prime. That means the GCD of A and M must be 1. In that case, to find the inverse modulo means we have to take an integers s and t. Here the inverse of A modulo M exists. That means there exists an integer s and t such that sa plus tm, which is equal to 1. Here to solve the inverse value for any number in a congruency, first we have to check the GCD of A and M are relatively prime or not. In that case, we can take an integer s and t such that sa plus tm, which is equal to 1. Here we have to obtain a value like this, that is sa plus tm, which is equal to 1. We are obtaining this value with the help of Euclidean algorithm. We are already discussed in the previous videos how to find the GCD with the help of Euclidean algorithm method. So we have to apply Euclidean algorithm method here, and we have to obtain the value like this, that is sa plus tm, which is equal to 1, where s and t are some integers, which implies sa plus tm, which is equal to 1. That implies sa plus tm, which is congruent to 1 under modulo m. This is same as this, sa plus tm, which is congruent to 1 modulo m. Next, but t into m is equal to 0 under modulo m, because obviously here t is an integer, m divides m satisfies, so tm, which is equal to 0 under modulo m satisfies. So this value becomes 0. That implies sa is congruent to 1 under modulo m. Here first we are taking sa plus tm, which is equal to 1 with the help of Euclidean algorithm method. Using this, we can write the congruency as sa plus tm, which is congruent to 1 under modulo m. Since tm is equal to 0 under modulo m, because m divides m satisfies, so tm value is 0. So substituting tm value 0, we get sa is congruent to 1 under modulo m. That is sa is congruent to 1 modulo m, which implies s must be the inverse of a under modulo m. Here sa is congruent to 1 mod m. If we take a to the right hand side, that is s is congruent to a inverse mod m. That implies s must be the inverse of a under mod m. Here inverse of a, that is a inverse is s. So we can conclude that s must be the inverse of a under modulo m. In this procedure, we have to solve the problems on Wilson's theorem, that is to find the inverse value for any numbers. In the similar way, using that proof, we have to find the inverse value for 6 by Euclid's algorithm method. Here first we have to find whether the GCD of a and m, here a value is 6 and m is 101 here, that is p value is m here. We know that we have to find the GCD of 6 and 101 is 1 or not. Obviously the GCD of 6 and 101 is 1, that is relatively prime, because 101 is a prime number. We know that p is a prime number, that is 101 is a prime number. So the divisors of 101, that is the divisors of prime number is 1. Therefore we can conclude that GCD of 6 and 101 is 1 here. We already discussed in the previous videos how to solve the GCD. Next we have to consider, or we have to divide 101 by 6. Here we have to divide the greatest value by the smaller value with the help of Euclidean algorithm method. Here we have to divide 101 by 6. We know that 6 into 16. 6 into 16 is 96, which is close to 101. Here if we take the value 17, which is a greater value than 101. Therefore, we have to take as 16 as a quotient, that is 6 into 16 is 96. Next step, we have to subtract 101 by 96. We get the value as 5. So 5 is a remainder when 101 is divided by 6. Next step, we have to divide this value 6 by the remainder 5. That is, we have to divide 6 by 5. That is 5 ones are 5. Therefore, we get 6 minus 5 as 1 as a remainder. Next, we have to divide this 5 value by 1. That is, we have to divide 5 by 1. That is, 1 into 5 is 5. So, we get 5 minus 5 as 0. So, once we obtain a remainder as 0, we have to stop here. Next step, we have to apply Euclidean algorithm formula over here. Here we have 6 is a divisor, 101 is a dividend, 16 is a quotient and 5 is a remainder. For this we have to apply Euclidean algorithm method. We get here Euclidean algorithm formula is dividend, which is equal to divisor into quotient plus remainder. Here 101 is dividend, 6 is a divisor, 16 is a quotient and 5 is a remainder. Therefore, we can write this as 101, which is equal to 6 into 16 plus 5, or we can write this as 5, which is equal to 101. We can take this value to the left hand side, that becomes minus of 6 into 16. Call this as equation number 2. In the similar way, we have to apply Euclidean algorithm formula for this. We get 6, which is equal to 1 into 5 plus 1. That is, 6 is a dividend, 5 is a divisor, 1 is a quotient and here 1 is a remainder. Therefore, we can write it as 6, which is equal to 1 into 5 plus 1, or we can write this as 1, which is equal to 6 minus of 1 into 5. Call this as equation number 3. Next, from equation number 3, we have to find the inverse value for 6. That is, we have 1 is equal to 6 minus 1 into 5. So, to find the inverse means we have to obtain an equation as SA plus Tm value, which is equal to 1. Here we have 1 is equal to some value. So we have to consider equation 3 and we have to find the inverse value for 6. That is, from equation 3 we have 1 is equal to 6 minus 1 into 5. Next step, here we have 5 is equal to 101 minus 6 into 16. So from equation 2, substituting 5 value as this, we get 6 minus 1 into, here 5 is 101 minus 6 into 60. Next step, multiply minus inside the bracket and simplify. We get 6 minus 101 minus 2 minus plus 6 into 60. Here we have 6 into 1. Here we have plus 6 into 16. Hence we get 6 as common means 6 into 1 plus 16 is 17. Therefore we get 6 into 17 minus 101 value, which is equal to 1 here. Or we can take this as 1 is equal to 6 into 17. Here take minus inside the bracket, we get as plus 101 into minus 1. Here we have to achieve this value or an equation as to form SA plus Tm value, which is equal to 1. So we have to apply here positive value. Therefore, multiply minus inside the bracket, we get as 1 is equal to 6 into 17 plus 101 into minus 1. Next step, what's the proof? Here m value is 101 here. So Tm value is 0 under mod m satisfies. Here 101 divides 101 satisfies. So we have to neglect this value. This value becomes 0. Therefore we get a value as 1 is equal to 6 into 17 under modulo 101, or we can write this as inverse of 6 is 17 under modulo 101. Here if we take this 6 to the right hand side, that becomes 17 is congruent to 6 inverse under modulo m. That implies inverse of 6 is 17 under modulo 101. Here this is a way to find the inverse value for any of the number under the congruency. Therefore, we can conclude the 6 inverse which is congruent to 17 under modulo 101. So from equation 1 we have 97 factorial which is congruent to 6 inverse under modulo 101. Here 6 inverse is congruent to 17 modulo 101, that implies 97 factorial which is congruent to 17 under modulo 101. Therefore, we can conclude that 17 is a remainder when 97 factorial is divided by 101. This completes the problem. Here the main aim is to find the inverse value for a given number under the congruency. So to find the inverse value means we have to apply the note value here, that is if A and M are relatively prime, that is the GCD of A and M value is 1, then the inverse value of A under modulo M exists. So first we have to check whether the GCD of A and M value is 1 or not. So next step we have to find the values, or we have to divide the bigger value by smaller value, and we have to apply Euclidean algorithm method here, that is dividend which is equal to divisor into quotient plus remainder. With the help of Euclidean algorithm we have to find the inverse value of any number under modulo M. So that value itself is a remainder when 97 factorial is divided by 101. This completes the problem. We shall move on to another problem so that you can understand in a better way. Find the remainder when 14 factorial is divided by 70. Here by Wilson's theorem we have p minus 1 factorial which is congruent to minus 1 under modulo p. Here we can apply this formula directly and simplify. Also we have another formula, that is extension of Wilson's theorem. We have another formula, that is p minus 2 factorial which is congruent to 1 under modulo p. Here this formula is also an important formula, you have to remember. Here one formula is p minus 1 factorial is congruent to minus 1 under modulo p. We can substitute p value here itself and simplify. Both formula are same. Or we can take another formula, that is p minus 2 factorial which is congruent to 1 under modulo p. I am using this formula here. You can use this formula also, both are same. Here we have to find the remainder when 14 factorial is divided by 17. That means 17 is a p, that is prime number. We know that 17 is a prime number, so p value is 17 here. Substituting p value is 17, we get 17 minus 2 factorial which is congruent to 1 under modulo 17. 17 minus 2 is 15 factorial which is congruent to 1 under modulo 17. Procedure is same as before. Here we have to obtain the remainder when 14 factorial is divided by 17, but here we get 15 factorial. So with the help of formula, that is n factorial is n into n minus 1 factorial. So substituting n value as 15, we get 15 into 15 minus 1 is 14 factorial. Therefore 15 factorial we can write this as 15 into 14 factorial which is congruent to 1 under modulo 17. Here we have to find the remainder for 14 factorial. So to achieve 14 factorial we can take this 15 to the right hand side or divide throughout by 15. We get 14 factorial which is congruent to 15 inverse under modulo 17. So procedure is same as before problem. We have to find the inverse value of 15 under modulo 17 with the help of Euclidean algorithm method here. Take this equation as equation number 1. Next step, you have to find the 15 inverse by Euclidean algorithm method. So procedure is same as before. First we have to check whether the 15 and 17 are relatively prime or not. Obviously 15 and 17 are relatively prime, that is GCD of 15 and 17 value is 1, because since 17 is a prime number, the divisors of 17 is 1 and 17 number itself. The divisors of 5 is 1, 3 and 15. Therefore among these two the greatest common divisor is 1. Therefore we can conclude that the GCD of 15 and 17 is 1. Obviously the GCD value is 1 here. Next step, we have to divide the greater value by smaller value, that is we have to divide 17 by 15. We know that 15 into 1 is 15. Therefore 17 minus 15 is 2 is a remainder. Next step, we have to divide this 15 value by 2. We get 2 into 7. Here 2 into 7 is 14. So 15 minus 14 is 1 is the remainder. Similarly, we have to divide 2 by 1. We get 1 into 2 as 2. Therefore, we get 0 as a remainder. We have to stop the procedure here. Next, we have to apply Euclidean algorithm formula for this value and for this value. We get here 17 is a dividend. Therefore, dividend which is equal to divisor into quotient plus remainder, or we can write this as 2 is equal to 17 minus 15 into 1. Call this as equation number 2. In the similar way, 15 is a dividend here. Therefore, we can write this as 15 is equal to 2 into 7 plus 1, or we can write this as 1 is equal to 15 minus 2 into 7. Call this as equation number 3. Next we have to consider equation 3 and we have to find the inverse value for 15. So from equation 3 we have 1 is equal to 15 minus 2 into 7. Next step we have to apply Euclidean algorithm method for 2 also. That is, from equation 2 we have to substitute in the place of 2 as 17 minus 15 into 1. Here equation 2 is this. Next step, simplifying the value we get 15 minus, here multiply 7 inside the bracket, we get 15 minus 17 into 7. Here minus 2 minus plus 15 into 1 into 7 is 7. Next step, here we have 15 into 1, here we have plus 15 into 7. So if we can take 15 as common, means 15 into 1 plus 7. Therefore we get 15 into 1 plus 7 is 8 plus 17 into minus 7. Here we can take minus inside the bracket because we have to achieve the equation SA plus TM is equal to 1. We have to apply plus sign. Therefore take minus inside the bracket, we get 15 into 8 plus 17 into minus 7. Here we have to apply this value for under modulo 17. Therefore this value becomes 0. Here 17 divides 17 satisfies. Therefore 17 into minus 7 is congruent to 0 mod 17. Therefore this value becomes 0. Therefore we get a remaining value as 1 is equal to 15 into 8, or we can write this as 15 inverse is congruent to 8 under modulo 17. Here you can take this 15 to the left hand side, we have 15 inverse which is congruent to 8 under modulo 17. Therefore we can conclude that 15 inverse value is 8 under modulo 17. From equation 1 we have 14 factorial is congruent to 15 inverse under modulo 17, which implies 15 inverse is congruent to 8, that implies 14 factorial is congruent to 8 under modulo 17. Therefore we can conclude that 8 is a remainder when 14 factorial is divided by 17. Here 8 is a remainder when 14 factorial is divided by 17. This completes the problem. These are all very easy problems. Only important thing is you have to apply Euclid algorithm method here and to simplify in the form of 1 is equal to SA plus TM. Next step, Tm value is 0, so we get the inverse value for a particular function. That's an important step here. Here is another problem. Simplify 130 factorial by 87 under modulo 131. Here this is the same problem as before. Here we have factorial, means we have to apply Wilson's theorem, that is confirmed. First step, we have to take this given problem as x, that is let x is equal to 130 factorial by 87 under modulo 131. Here 130 factorial divided by 87, we can take this to the numerator, we get x is congruent to 130 factorial into 87 inverse under modulo 131. Here 1 by 87 is same as that of 87 inverse under modulo 131. So by Wilson's theorem we have p minus 1 factorial is congruent to minus 1 under modulo p. Here p is a prime number, here 131 is a prime number, so we can take p values 131 here. Substituting p values 131, we get 131 minus 1 is 130 factorial is congruent to minus 1 under modulo 131. So here we have x is congruent to 130 factorial into 87 inverse under modulo 131. Here we get, by the help of Wilson's theorem, 130 factorial is congruent to minus 1 under modulo 131. So in the place of 130 factorial we can write it as minus 1. That's the next step. Therefore we get x is congruent to, here 130 factorial is minus 1 into 87 inverse under modulo 131. Now we can call this as equation number 1. Next step, we have to find the inverse value of 87 and substituting over here we get a value of x. That's the procedure. That is, we have to find the inverse value of 87, that is 87 inverse by Euclid's algorithm method. So first step is to verify whether the GCD of 87 and the value 131 is 1 or not. Obviously the GCD of 87 and 131 is 1, because since 131 is a prime number, the only divisors of 131 is 1 and 131. So among these two the greatest common divisor is 1. Therefore the GCD of 87 and 131 is 1. Both are relatively prime, satisfies. Next step, we have to divide the greater value by 87. So we have to divide 131 by 87. So we get 87 into 1 as 87. Next step, 131 minus 87, we get a value as 44. Next we have to divide this divisor value 87 with a remainder 44. We get, here we have to divide 87 by 44. Therefore we get 44 into 1 as 44. So if we take a value as 2 means 44 into 2 as 88, which is greater than 87. So we get 44 into 1 as 44. Next step we have to subtract 87 by 44, we get a value as 43. Similarly, we have to divide this 44 by 43, we get 43 into 1 as 43. Remainder is 1 here. Next step we have to divide this 43 by 1, we get 1 into 43 as 43. Therefore we get 43 minus 43 value is 0. We have to stop value here. Next we have to apply Euclid algorithm method for this. Here also we have to apply Euclid algorithm formula. Here also we have to apply Euclid algorithm formula. Therefore from this factorization we have 131 which is equal to 87 into 1 plus 44, or we can take this as 44 is equal to 131 minus 87 into 1. Call this as equation number 2. In the similar way for this we have 87 which is equal to 44 into 1 plus 43, or we can take this as 43 is equal to 87 minus 44 into 1. Call this as equation number 3. Similar way for this we have 44 is equal to 43 into 1 plus 1, or we can take this as 1 is equal to 44 minus 43 into 1 and call this as equation number 4. Next step, procedure is same as before. Here we have to take the equation 4 because this of the form 1 is equal to SA plus TM form. So to obtain that form, we have to take the equation 4 and substitute all these values here. We have to apply the inverse value for 87. That's the procedure. So from equation 4 we have 1 is equal to 44 minus 43 into 1. Next step, from equation 3 we have to substitute in the place of 43 as 87 minus 44 into 1. Next, multiply negative sign inside the bracket and simplify. We get 44 minus 87 into 1. Here minus to minus plus 44 into 1 as it is. Here we have 44 into 1. Here also we have 44 into 1. We have 44 into 2 minus 87 into 1. Next step, we have to substitute from equation 2 in the place of 44 as 131 minus 87 into 1, because 44 value is this. From equation 2 you can substitute 44 value as this. Next step, multiply 2 inside the bracket and simplify. We get 131 into 2 minus 87 into 2 minus 87 into 1. Here we have minus 87 into 2. Here we have minus 87 into 1. We get a value as 131 into 2 minus 87 into 2 plus 1 is 3. 87 into 3. Or we have to achieve this here as a positive sign. Therefore, we get 131 into 2 plus 87 into, take minus inside the bracket, we get minus 3. So this is of the form 1 is equal to SA plus TM. Here under modulo 131, so this value becomes 0. Therefore, we get 1 is equal to 87 into minus 3. Therefore, we can conclude that 87 inverse is congruent to minus 3 under modulo 131. Here 1 is equal to 87 into minus 3. Take 87 to the left hand side, that becomes 87 inverse, which is congruent to minus 3 under modulo 131. So we have to substitute 87 inverse as minus 3 from equation 1. Therefore, we can take this as x is congruent to minus 1. Here in the place of 87 inverse we can take this as minus 3. So we get minus 3 under modulo 131. That is x is congruent to minus 1 into minus 3, that is positive value of 3. That is x is congruent to 3 under modulo 131. Therefore we can conclude that 3 is a remainder when 130 factorial is divided by 131. This completes the problem. We shall move on to another problem. Simplify 146 factorial under modulo 149. So procedure is same as before. Take this value as x is congruent to 46 factorial under modulo 149. So call this as equation number 1. Next step, by Wilson's theorem we have p minus 1 factorial is congruent to minus 1 under modulo p. Here p is a prime number, that is 149 is a prime number. Therefore substituting p values 149, we get 149 minus 1 is 148 factorial, which is congruent to minus 1 under modulo 149. Here we have to simplify for 146 factorial, but here we have 148 factorial. So to achieve this value as 146 factorial, as before, you can write this 148 factorial as 148 into 147 into 146 factorial, because n factorial is n into n minus 1 factorial. With the help of that factorial formula, we can write this as 148 into 147 into 146 factorial, which is congruent to minus 1 under modulo 149. Here this is 148 is also a bigger number, 147 is also a bigger number. So we can write this as, here 148 is congruent to minus 1 under modulo 149. In the similar way, 147 is congruent to minus 2 under modulo 149, because 148 congruent to minus 1 under modulo 149, that is implies 149 divides 148 minus 2 minus plus 1. Therefore, we get 149 divides 149 satisfies. So in the place of 148 we can substitute as minus 1. In the place of 147 we can substitute as minus 2. Here minus 1 into minus 2 is plus 2. If we take this plus 2 to the right hand side, that becomes 146 factorial, which is congruent to minus 1 as it is into 2 inverse under modulo 149. We obtained these values. Call this as equation number 2. Next step, we have to substitute this equation 2 in equation 1. Here we have equation 1 as x is congruent to 146 factorial under modulo 149. Here we have 146 factorial is congruent to minus 1 into 2 inverse under modulo 149. So substitute in the place of 146 factorial as this, we get x is congruent to minus 1 into 2 inverse under modulo 149. So substituting equation 2 in equation 1, we get a value as this. Call this as equation number 3. Next, we have to find the inverse value of 2. That is to find the 2 inverse by Euclid's algorithm method. First step, we have to check whether the GCD of 2 and 149 value is 1. Obviously, the GCD of 2 and 149 value is 1 because P is a prime number, that is 149 is a prime number. So divisor of 149 is 1 and 149 itself. The divisor of 2 is 1 and 2. Therefore, among these two, the greatest common divisor is 1. Therefore, the GCD of 2 and 149 is 1. Next, we have to divide 149 by 2. We get here 2 into 74 value is 148. Next step, subtract 149 by 148, then we get a remainder value as 1. Next, we have to divide this 2 value by 1. We get 1 into 2 as 2. So subtract 2 and 2, we get a remainder as 0. We can stop here and we have to apply Euclid algorithm formula for this. We get 149, which is equal to 2 into 74 plus 1. Or we can take this as 1 is equal to 149 minus 2 into 74. So this is because dividend is equal to divisor into quotient plus remainder. That's a formula of Euclid algorithm. So next, call this as equation number 4. Next, with the help of equation 4, we have to find the inverse value for 2. Here equation 4 is 1 is equal to 149 minus 2 into 74. Next, we have to achieve the value as 1 is equal to SA plus TM. So take minus inside the bracket, we get 1 is equal to 149 plus 2 into minus 74. So this is value under modulo 149. So we get 149 value as 0 because 149 is congruent to 0 under modulo 149. Therefore, we get 1 is equal to 2 into minus 74. Take this 2 to the left hand side, we get 2 inverse is congruent to minus 74 under modulo 149. Next step, we have to substitute 2 inverse as minus 74 in equation 3. So from 3, we have x is congruent to minus 1 into, here 2 inverse values minus 74 under modulo 149. Here minus into minus plus 74. Therefore, we get x is congruent to 74 under modulo 149. This implies 74 is a remainder when 146 factorial is divided by 149. This completes the problem. Here is another problem. Show that 4 into 29 factorial plus 5 factorial is divisible by 31. Here, factorial form means we have to apply Wilson's theorem. Similarly, in this problem, we have to show that 4 into 29 factorial plus 5 factorial is divisible by 31. This implies we have to show that 4 into 29 factorial plus 5 factorial is congruent to 0 under modulo 31. That's the method here. So by Wilson's theorem we have p minus 1 factorial is congruent to minus 1 under modulo p. Here we have 31, that value is p here. Here we have 29 factorial. So to achieve 29 factorial directly, I am applying another formula, that is p minus 2 factorial is congruent to 1 under modulo p. So substituting p values 31 means 31 minus 2 is 29. We can directly obtain the value. So we have to substitute p values 31 for this formula. We get 31 minus 2 factorial is congruent to 1 under modulo 31. 31 minus 2 is 29 factorial is congruent to 1 under modulo 31. Here we have to show that 4 into 29 factorial plus 5 factorial is congruent to 0 under modulo 31 because we have to show this value is divisible by 31. So in the next step, we have 29 factorial here. We have to multiply 4 for this congruency, that's the next step. Here we have 29 factorial, but we have to obtain 4 into 29 factorial plus 5 factorial. For that, first multiply throughout this congruency by 4. We get 29 factorial into 4, that is 4 into 29 factorial, which is congruent to 1 into 4 is 4 under modulo 31. Also, we have to add this 5 factorial. Next step, add both sides of a congruency by 5 factorial. We get 4 into 29 factorial plus 5 factorial, which is congruent to 4 plus 5 factorial under mod 31. Here in the right hand side we have 4 plus 5 factorial. So we know that 5 factorial is nothing but 5 into 4 into 3 into 1. This 5 factorial is 5 into 4 into 3 into 2 into 1. Therefore we get 5 factorial value as 120. 120 plus 4 is 124 in the right hand side. Therefore we get 4 into 29 factorial plus 5 factorial, which is congruent to 124 under modulo 31, because 5 factorial is 120 plus 4 is 124. Next step, here 124 is under modulo 31 means we can divide 124 by 31. So we have to divide 124 by 31. We know that 31 into 4 is 124. 31 into 4 is 124. So subtracting 124 by 124, we get a remainder value as 0. Therefore, we can write 124 as 0 because 124 is congruent to 0 under modulo 31. Therefore, substituting 124 value as 0, we get 4 into 29 factorial plus 5 factorial, which is congruent to 0 under modulo 31. This implies 4 into 29 factorial plus 5 factorial is divisible by 31. This implies 31 divides 4 into 29 factorial plus 5 factorial minus into minus 0. This becomes, so this also implies 4 into 29 factorial plus 5 factorial is divisible by 31. Both are same. This completes the problem. So till here we studied some of the important question paper problems on Wilson's theorem. In next video we study about Euler's torsion theorem and problems related to that. If you have any doubts regarding this topic, comment below. Thank you.